Okay, let's get started. So, starting last lecture, we started to discuss ion transport. So essentially, we want to understand what are the factors that govern the ion motion in solid or ionic crystals. So we talk about two things. So if we talk about ion transport, we have two things. The first is diffusion. Again, diffusion is driven by either you have the concentration gradient partial C partial X, or in principle, it can be chemical potential gradient. So this is basic diffusion. And we have the rules that govern the diffusion, which is Fick's first law. So basically, we have the flux is basically linearly proportional to the driving force. Basically, J, which is flux, is diffusivity times the driving force, which is concentration gradient. So the second thing is we also have drift. So basically, these are charged ions. Essentially, let's say if I have ions, which is positive V of charge, if we have the electric field, then it will move with the direction of the electric field. Okay. So then the driving force for that is the electric field. So that's basically the negative of the electrostatic potential. Okay. So as you can see here, there's always a negative sign in front of the driving force because think about diffusion, the materials or the ions will move from where you have high concentration to the low concentration. Same thing with the drift. Of course, for drift, we have the Ohm's law. So basically, now the this is current density or the flux of charge. Then this is driving force. To correlate these two, we have the conductivity. Okay. So, however, since we are dealing with ions, it can be that we have these two things coexist. Okay, so basically we can have the case where we have a drift and diffusion at the same time. So essentially, last lecture we spent a long time to discuss what that quantity should be. Okay, we want to have a kind of unified picture that can include both diffusion and drift. I think for this we might want to write all this equation again, since it has been quite some time since we had the last lecture. So essentially, if we have some species, for some species I can be some ions or some electrons, then the diffusion is basically here for the Fick's second law, be minus D partial C partial X. However, we want to convert that to the driving force represented by chemical potential. So we want to write something like this. So basically, I want to write partial mu partial X. Of course, to have from here to here, we times partial mu partial C here. Okay. We know that. Let me erase that part. We know that mu is essentially linked to the concentration using this equation, right? So partial mu partial C. Of course, here we already say it's a dilute limit. Otherwise, you have activity right than concentration here. Okay. Then the partial mu partial C is RT over C. Okay. So basically, you apply this thing into this equation, what you get is basically negative CD over RT partial mu partial X. Okay. So this is basically the first equation we want to talk about. Let me put I okay. So basically, I write again. So for this diffusion, would be something like minus di di RT partial mu I partial X. Okay. So we also know that we have drift, which is gotten by Ohm's law. Okay. So if we have drift, then Ji drift. So basically, we know that this is the flux of charge, right? We want to convert to that flux of the particles. So we want to say, okay, so it's Ji, this is basically charge or the current density, divided by dn. Okay. So basically, we get sigma over dn, sigma I over di f negative then partial pi partial x. Okay. So this is basically the second equation. We have the drift flux. Should be something like sigma I di f partial phi partial x. Again, I is some kind of species, or can be ionic or electronic, right? So it can be something like oxygen ions, it can cations, or it can be electrons or holes. So any ionic or electronic species will follow these two equations. Okay. So we are not really specifying which particles we are dealing with. Then we have the total. And basically we add these two up. Okay. Ji drift. First diffusion. Drift. Okay. So we basically want to add these two things up. However, we need to supply two important equations to kind of have this kind of have the elegant form for the flux. So which are the representation of the conductivity. Okay. So conductivity essentially should be let's say Ni times Zi times mu. Okay. And basically the number of charge carriers, basically number of ions or electrons. Then this is how many charge, how much charge does one particle carry. Then this is big mu, which is the mobility. However, we are more used to represent it by concentration. Okay. If we change from this one to this one, you basically divide by Avogadro constant. So basically, number of particles is concentration times Avogadro constant. Okay. Then if we times Na with the charge, we get a Faraday constant. Okay. So then we can write it something like this. So this is basically what we usually use for conductivity. Okay. So this is the first equation. The second one is basically Nernst-Einstein equation. So Nernst-Einstein equation it basically tells you that the diffusivity and mobility, they are essentially the same thing. So they differ by only a constant. Okay. So because we know RT is a constant, Faraday constant is constant, then Zi is fixed for any particular ions or electronic species. So it's basically saying that under kind of small or not too large driving force, then the drift and diffusion, they are essentially describe the same picture. So in today's class, we'll learn more on this, why that is true. Okay, so what we can do is we can go back to this equation and write a little bit more. Okay, so we want to write two things. First, we don't like the diffusivity here. Okay, so we want to change it to something like mobility. Okay, if I want to change it to mobility, then di is mu times RT over Zf times RT over Zf. And RT here, partial mu, partial x. Okay. And you can see the RT basically cancels out. Okay. And we have another one, which is the drift. So I'll write Zi square F square, then partial Z I F phi partial X. Okay, so this is the second term here. So what we can do is we also put a square here. Okay. Then what we can do is we times Zi F. And you recognize this part is basically conductivity. Okay. So then we have this very nice form. Zi square F square sigma I. Okay, so this is basically the common part. You see, we have this part, and we have this part. Okay. Then what's left is in the as the driving force. Partial X. So you can see that this is basically the J. Okay, so this is basically the JI. Okay. You can see from this equation, what really matters is this part. So this is the real driving force. We call it mu I tilde being mu I plus Zi F phi, which is called electrochemical potential. So we can essentially go back here and add one more equation to this one. So if I say, just say this is J total, okay, which means that we consider both diffusion and drift, okay, then we know that this part is driving force. So basically, this column is driving force, okay. Then we know that if we have both diffusion, which is concentration or chemical potential gradient, and also drift, which means electrostatic potential gradient, then the real driving force will be the gradient of electrochemical potential. Okay. So what in front of this is basically some kind of conductivity. Of course, there is a constant here. Okay. So this is basically a very important equation. So this really governs. So basically, this is true always, right? So no matter whether you have only drift or only diffusion, you have this equation. Okay. So of course, if you look at this, if say I say J is sigma over Zi phi, Z square F square partial mu tilde partial X. Okay. If we say the so any this kind of principle or equation should reduce to the kind of special case, right? So if I say I is something like a charge neutral species, for example, charge neutral oxygen or charge neutral lithium, okay, right? Then in this case, mu tilde, this basically say that Zi is 0, okay. Then the mu tilde should be just the mu, so which means that for any charge neutral species, you don't have the electrochemical potential is basically the same as the chemical potential, right? So you cannot drive the motion by using the electric field. Okay. Then this is really should reduce to the fixed first law. Okay. Let's see if that's the case. Okay. So if we say, okay, if of course it's a little bit tricky to define the conductivity for charge neutral species, right? So there's no real conductivity. There's only a diffusivity. But anyway, so if that's the case, we have negative sigma is basically this thing here. Okay. So C df mu d square f squared. Okay. So this part is basically the because I assume the charge is 0, So this part will reduce to only chemical potential. Right, so then of course this part reduces, then we convert from the mobility to diffusivity here. Then finally we have C mu is di over times this over RT, right? So d times df over RT, and we have df here, which cancels out, partial mu plus x. So you can see that if we don't have any charge for charge neutral spaces, it will reduce to what we had in the beginning. Okay, which means that, so this is a kind of difficult way to show. Okay, so this should apply to any system, whether you have only diffusion or you have diffusion and drift. So of course, we know that. So if we reach equilibrium. At equilibrium, then the flux should be 0. Then the condition gives you partial mu I, partial x. It's basically 0. Okay. So this is basically the equilibrium condition. Okay. So one of the application for that is in electrochemical devices. Either a fuel cell or a battery we talked about last lecture. So essentially at the equilibrium, for example, if I have a battery, so we have electrolyte in the middle, then the cathode and the anode. Then if we measure the open circuit potential, which means that there's no net flow of charge, then in the electrolyte, we have, for example, if it's a lithium-ion battery, then we have the electrochemical potential for lithium-ion should be, there should be no gradient, which means the electrochemical potential should be the same everywhere in the electrolyte. So last lecture we also derived the very important thing is to say the open circuit potential, open circuit voltage for such a device will be the difference between the electrochemical potential of the electrons. Okay. So this is because that's how we measure, right? We use a multimeter to measure between the cathode and anode. And then so basically, if we have the electron flow through the multimeter, it is the difference between electrochemical potential of electron which determines which is served as a driving force, right? So that's why the OCV is directly linked to the difference in the electrochemical potential of electrons. However, if we apply this, and last lecture we showed that this can be directly related to the chemical potential of lithium. So this is charge neutral space of lithium in the cathode and in the anode. Okay, and of course you can link that into the sorry, it's not standard. Basically the reaction chemical potential or gauge free energy of reaction per mole. Okay, so I'm not going there. If you want to check details, you can check the slides I sent you. Okay, so any questions regarding the what we talked about last lecture, because it has been quite some time ago. Okay, no? Okay, so essentially what we talk about here are the so-called microscopic picture. Essentially, we are not really going to the details regarding the ion transport, right? I didn't tell you atomistically how the ion diffusion really happened, or what's the detail regarding the drift, right? So in today's lecture, we are going to focus on the so-called microscopic picture of ion transport. Okay. So essentially, in atomic scale, so how does the drift and diffusion happen for ions? Okay. So first, we talk about diffusion of ions. We already said some things about the diffusion because it's quite different from the, for example, the ion diffusion in liquid or gas molecule diffusion in gas phase. For diffusing ions in ionic crystals, there has to be rely on defects. Okay. So if you think about different atomistic picture, there are essentially three different kinds of mechanisms. So the first one is that you can have, for example, vacancies. Okay. So basically, you have vacancy. So you can imagine that the ions basically jump from the regular side to the vacancy. Then the end of result is that you have this kind of sparking mechanism. So something like this. Okay. So then you have vacancy here, and then the jumping can be can just go up. Of course, the jump is kind of random, right? So the ions here can have the same probability of jumping back, right? So because here we assume that every ions here are the same. Okay. So it's basically a vacancy mechanism. So you can also have something like a interstitial. So essentially, if you have interstitial here, so it's interstitial. So it can jump from here to here. Okay, I'm now drawing another picture. I'm just showing in this. Okay. So vacancy mechanism is very common. For example, if you have something interesting like zirconia, so-called YZ, so what you do is you introduce kind of dopants, 3 plus yttrium into 4 plus of zirconium, then you essentially introduce oxygen vacancies. Then the motion or the diffusion of the oxygen is basically driven by that. Okay. So interstitial is probably less common. So one of the case is so-called RT phase oxide. So for example, if you have less than nickelate, so but it's not perovskite, it's so-called 2-angle phase. So one way to think of it is that you have one layer of perovskite, then another layer of rock salt layer. The rock salt layer is basically the less than oxide. Okay. So you can have oxygen over stoichiometry in this rock salt layer. Then you have for example, this is the oxygen interstitials, then you can really jump. Okay. So another very special case what people found is so-called interstitial C. Okay. So it's different from interstitial. So what it describes is kind of concerted motion. Essentially, if you have interstitial defect here, it can really knock one ions, then move this to the interstitial site. So its ions basically jump into regular site, but the regular ions jump into this site. Okay. So in some special cases, you can have something like this. Some researchers believe that in RB phase oxide, you already have interstitial C. But in other cases, for example, if you introduce protons into the nickel oxide, you can have this case, something like that. I'm not really going to more details here. Okay. So anyway, doesn't matter what you have. So you can see the common thing of the ion transport or diffusion is that you have this kind of two similar configuration. For example, if you think of this as the starting or the initial state, so this thing is your final state. So sometime in the in between the two states, there'll be a moment that ion is kind of in this intermediate position. Usually, when ion is in the intermediate position, it kind of really perturbs the ion potential of the lattice, and the energy really goes up. So essentially, we have. So if you think that if you have ion here, and if you have vacancy here, then if you jump from here to here, in the middle, you have to overcome some kind of barrier. So essentially, you can draw a very simple picture, is that you have two, this might be so-called initial state. So this is your final state. They should be the same, okay. Then in the middle, so you have to overcome some kind of barrier. So usually it's so-called migration enthalpy. Okay. So it really should be migrational Gibbs free energy, but we kind of neglected the entropic contribution. Okay. So since it has to overcome the barrier, so of course it's somewhat activated. So the picture is if you have ion here, okay, then any vacancy here. So it'll have so there'll be some kind of lattice vibration. Let's see. So lattice vibration basically kind of drop the ions. Kind of near this initial state, right? Then you will attempt to jump to the other side, overcome the barrier. Okay. So usually what we use is we use something called a mu. This basically is the kind of attempt frequency. So basically that means that per second, how many times ion is trying to jump over to the other side. So, of course, only very few jumps can succeed, can overcome the barrier, okay, to the other side. So we have some kind of exponential function to really evaluate how many percentages of the jump will be successful. Okay. So this is basically successful rate. Okay. So then the total thing we call it tau. So that's basically hopping frequency. Okay. So attempt frequency is basically in the unit of hertz or in the unit of per second. Okay. So this is doing this. So the hopping frequency is also in hertz. Okay. So you can see that the higher the delta H is, the smaller the successful rate. Any questions?
No. 帮我解释一下那个 delta H 这个它是指的？
So the delta H is basically from the highest point, right? So basically the ions jump from here to here, right? So there has to be a kind of middle stage where the system edge is high. Okay. You can imagine is that the ions is kind of in a periodic potential because it's kind of a lattice, right? So if you jump from here to here, in the middle, ions sitting in a kind of inconvenient position, right? So it has to be somewhere here. Okay. So what you can see is that the higher temperature is, the higher the successful rate is. Okay. Also, if you lower the delta H, if you lower the barrier, for example, if you lower the barrier, then of course this becomes the success rate becomes higher. Okay. So what I'm going to do is I can give you some examples on the delta H, how much that is. Okay. So the migration barrier. So this is basically the migration barrier. So basically, if ions is trying to jump from here to here, what kind of barriers need to go come? For example, taking the YZ as example, if you would think of oxygen vacancy of oxygen ions in YZ, delta H is roughly 1 electron volt. Okay. We know that kBt is only 26 milli eV. Okay. So if you divide this by that, then if you take exponential, you'll find the success rate to be very, very small. So the reason why the YZ can only conduct oxygen ions at high temperature. Okay, so another example is if you think of lithium ion transport in solid-state electrolyte or solid-state batteries, then the migration barrier is of course much lower. It can be something like 0.2 UV. Okay. So now you can see that this is much better, right? So if you divide that by the room temperature kBt, the thermal activation, you have a better chance. Okay. So another thing is if you think of the colors in ceramics. For example, if you think of the for something like Syria, if you think about serum colorings in oxide, it has very high migration barrier. So the migration barrier can be something like 6 to 8 eV. Okay. So why is that important? So this will determine partially when you sinter your ceramic powder into bulk ceramic sample. Okay. So if you want to sinter it, then very importantly, the cation has to move to go to the kind of site for the cations. So that's why you need to care about the migration barrier for cations. Now usually cation migration is really difficult, then that's why if you sinter the ceramic sample, you have to go to very high temperature, something about 1200 degrees C, or even 1400 degrees C in extreme cases. Okay. All right. So this is basically the kind of picture. So we use microscopically how to understand the diffusion of ions. Okay. So then we want to see how to come from this part to the fixed first law. So because we know that first law is right, any microscopic picture has to give us the same results. Okay. So we're going to see how we can derive the fixed first law from this microscopic picture. So basically, we are looking for explanation of fixed first law from this microscopic picture. Okay. So again, what we have is, let's say, we have two positions, right? So we have either ions here, or either weakly here. So what we want to do is like we want to imagine in a one-dimensional case. Okay, so we first think about just only very simplified one-dimensional, then we kind of extrapolate to three-dimensional. Okay, so if I say this is the kind of reaction coordinate x, okay. So if I say this is position 1, so this is position 2, okay. So let's say if I have, you can think of as a column of the ions, right? So you can think about into the board, we have many ions here. So we have different concentrations, right? So for example, here we have concentration in C1. Here we have concentration in C2. Okay. Now, of course, diffusion is happening this way. We have J. Okay. So it should be a net flux. Okay. So how to evaluate J? So we know that we finally want to have some kind of expression for the flux. So basically the diffusion from here to here, right? However, we can have both ways, right? So we can have both ions jump from here to here, or ions jump from here back to here, right? So J is basically from 1 to 2 minus from 2 to 1. Okay, so this is your net flux. Okay. Then what we want to evaluate is we kind of cut a plane in the middle. Let's say the area is A. Okay. So we know that we have this kind of lattice, we have this kind of interatomic distance, basically how far the ions jump from one side to the other. Let's say it's atomic distance is A. Okay. Then we are trying to count how many ions jump from position 1 to 2, and how many ions jump from 2 to 1. So if we know this 2, then we can calculate the net flux. Okay. So from 1 to 2, we can say first we count a kind of we draw a box. So imagine that we have this part as the distance A, right? So this part we can kind of imagine how many ions in this box. Okay. So in this box we have this is A. Okay. So the number of ions located at the position 1 is basically N1. Okay. Then N1 they are kind of in this location 1. Okay. They start to jump. It can either jump from 1 to 2, or it can actually jump this way. Because imagine that, so this kind of is kind of periodic, right? So because it's ionic crystals, it can go both ways. It can go this way, or it can go that way. Okay. So it can jump from here to here, or it can also jump from here to here. Okay, so you have to put a 1/2 here. Okay. And finally, if you think of the hopping, I mean, it can go from here to here, but only but if you think of the successful rate, not every jump is successful. Okay. The successful hopping frequency is basically this one. Okay. So finally, you have to time it by hop. Okay. So if you think of the number of ions, we can assign to the position 1, basically all these ions in this box, right? So basically 1/2, then first we use a concentration, then we times by the volume of this box, right? So for the volume, we always say that this kind of area we cut into the board is A. Okay. So this part is small a. So the volume is A times small a. and of course we have to times tau. Okay, so this is basically the first equation here. Okay, then we have from 2 to 1, it's essentially the same. Okay, the only difference is now the concentration is not C1, it's C2. Okay. Then we have the J is from 1 to 2 minus from the 2 to 1 is basically 1/2, then C1 minus C2, A times A times tau. Okay. Sorry, I think I made a mistake. Okay. So basically, the flux is actually evaluated per area. Okay. So if you use the total number of ions, you have to divide it by the per area A. Okay. So if you divide by per area A here, it basically cancels out. Okay. Okay. So I remove here. And okay. So then we can have actually the flux, which has this expression. What we want to do is want to divide it by A from bottom end to the top. Okay. So let's say if I have C2 minus C1 and A squared tau here. Okay. So what you can recognize is that this part is basically the concentration gradient. Okay. So because we say, okay, so this concentration gradient is essentially, if we assume that's linear, that's basically the difference between C1 and C2 derived by interatomic distance. So this part is basically concentration gradient. Okay, so then we do a little bit cleanup. It'll be something like 1/2 A squared tau times partial C partial X, or in this case partial X is basically A, right? So we only have two positions. The delta X is basically A. Okay, so if you compare this with the Fick's first law, you can already see this is basically another form that we can have Fick's first law. Okay, so basically this part is basically your diffusivity. Okay, so this part is basically your concentration gradient. Okay, so now you have D is 1/2 A squared tau. Okay. And you can write a little bit more. If you consider tau is something over there, you can see it's A squared mu exponential. Okay, so this is basically we call it D0. Okay. So as you can see here, you have the kind of atomistic explanation of Fick's first law, right? So, and also you have the atomistic picture of the diffusivity. You can see that diffusivity is related to two things. First is of course the Hawking rate, right? So this is kind of intuitive, because the higher the Hawking frequency, the higher the successful Hawking frequency, you should have the higher diffusivity. So it also has something to do with the interatomic distance, right? So this is kind of also it can also be understood, because the way you measure the diffusion is that imagine if you have ion here, right? So ions can really hop here from here because it's kind of random, right? So each case you have these kind of atomic distance, because ions can only jump with just each case can only jump with one interatomic distance to the other side. Okay. So the way to measure the diffusion is basically finally, on average, how far away is the ion from the original position. Okay. So determining from 1 to 2, you have the successful rate, which is, or the hopping rate, which is gamma, right? Which is determined from this position to that position. Okay. Now finally, if you measure in average how far away ion has diffused, right? So it has kind of correlation both to the success rate, basically the hopping frequency, and also each case you have how far the ions can hop. Okay, that's basically the interatomic distance. Alright, so that's basically the kind of microscopic picture on the diffusion. Essentially, if we have J is some kind of partial C, partial X. However, so remember that here we only imagine that's one-dimensional, right? We know that in reality, it's not really dimensional. We have three-dimensional. We have different structure for ionic crystals. For example, if you think of three-dimensional, so the here we basically say why we have the one half, because ions can hop to this side or to the other side. So that's why we have one half here. Okay. But imagine if you are in three-dimensional, the ions can hop this way, or can hop that way, or it can hop this way. So it can be you have 6 probabilities. So in real ionic crystals, things are more complicated because so imagine if you have some kind of specific ionic structures that has something to do with the coordination number. Usually people use Cn as the notation. It basically says that how many possibilities ion can hop to the nearest neighbor. Okay. So that's why what we use is we put a Cn here. Okay, so this is basically the diffusivity. And we know that diffusivity is somewhat activated and limited by the hopping or the migration barrier. Okay. So the second thing we want to talk about the drift. So for diffusion, we have this kind of picture. We have initial state and final state. So they are essentially pretty much the same, right? So which means the level for the initial state and final state, they are on the same level because they are just two sides in the atomic structure. However, for drift, that's not really the case. Okay. So you can imagine that in the beginning, so you have this kind of barrier, right? So you can imagine you can have ions here or ions here, or you have the wiggle here, doesn't matter. So in the beginning, you have these two levels, they are the same, they are on the same level, okay. However, for drift, we know that we are applying the electric field, okay. So what the electric field does is can actually cause a change of the phi. So which means the electrostatic potential. Okay. For example, if I apply if I apply electric field that way, so you have let's say if the E is a constant, then we'll have something like this for the electrostatic potential. So of course, again, I'm going to draw two positions, 1 or 2. Then we can calculate the difference. Okay. So the difference for phi, again, I'll call interatomic distance as A. Then this part is basically first how much charge you have, right? So for example, if the charge of ions is E. Any questions? Then it times D times the phi, basically the on the electric field, then times the distance. So this is basically the how much difference you have. Okay. So of course, if you come from here, then so this half will be half of the E times A. Okay. So if you times the electric field with the distance, that's basically how much work you do. That's basically the electrostatic potential. Okay. So then, what you're going to change is you're going to change the energy landscape. Okay. So you see that you have more energy here, less energy here compared to this position. So then essentially you can imagine that these two positions, they are not the same anymore. Okay. So basically, so this is definitely exaggerated, but I'll show something like this. Okay, now you have something like this. Okay. Again, so this position 1 between 2, and we know there's a difference of energy between these two. Okay. And electric field is this way, and we know that now, so if you just look at this plot, you will see that the barrier here is actually lower, okay, than the barrier here, okay. From 2 to 1, the barriers become higher. From 1 to 2, the barrier becomes lower. So that's why for drift, it's different from diffusion, right? For diffusion, the ion can jump from here to here, or from here to here. They have the same probability. However, for drift, it's basically directional, right? So if I apply electric field, if we talk about cations, then we'll definitely go that way, right? That's how you have the current. Okay. So then what we are interested is basically calculate if we apply the electric field, how much is that changes the energy landscape. Okay. First of all, let's see how much this thing can be. Okay. So since we are trying to change, it's basically this term. Okay. So for example, if we have a cation, something like lithium, then we have DE times A, or half of the times A, if you think about that. Because if you come from here, looking both ways, you have half of this value. Okay. So let's say if we have lithium, then D is 1, right? Then of course this is electron charge, and if we say A is based interatomic distance, I mean usually it's in nanometer. Let's say it's 10⁻⁸ meter. Okay. Then we can basically calculate that. So this energy, okay. So this energy will be 1/2 times E times 10⁻⁸ meter. Then for the electric field, so let's imagine if you have a piece of sample. Okay. So you have a piece of sample with kind of dimension or thickness of D. So what you do is you put 2 electrodes on both sides, and you apply a voltage. That's how you have electric field, right? So then the electric field is basically, in this case, is basically the voltage divided by the thickness, right? So if I say if I say the voltage you apply is 10 volt, it's not small, it's already pretty big, right? So if the distance I applied is basically, let's say 1 centimeter. Okay, so basically you have 1 centimeter thick pellet, ceramic pellet, or single crystal, and you apply 10 volts on both sides. That's basically the electric field. Then the value is 10 volts per 1 centimeter. Okay. And let's calculate how much that is. Okay, so 1/2, I basically neglect 1/2, right? E is basically the charge. So one very convenient, you can put an E here. Then EV is essentially energy. Okay. Then you have 10 to the minus 8 meter. So that's basically the 10 nanometer, right? And the interatomic, 10 nanometer doesn't make sense. Let's say 1 nanometer, right? Because your lattice won't be that much. Okay. Let's say 1 nanometer is basically 10 to the minus 7 centimeter. Okay. So then the thickness of the somewhere is just 1 centimeter. Okay. This thing you can see is 10 to the minus 7, 1 thing here is roughly 10 to the minus 6 eV. Okay. So is this a large or small value? It's very small, right? Because we know that KBT it's only 26 millieV. Okay. However, for KBT, it's much larger than this value. Okay. And so this thing, this Magellanian barrier, we say for oxygen in YZ is something like 1 eV. Okay. So 10 to the 6 order of magnitude higher than this one. Okay, so that's why I'm saying that this is really an exaggeration, right? So in reality, which you can see only the tiny bit of difference in this case, right? So in this case, it's only the E. It's only 10 to the minus 6 eV. So it's tiny compared to this one. Although it's tiny, it has created asymmetry, right? So which means, so this level is only slightly higher than this one. Okay. So you can imagine that you create a little bit higher than that, a little bit higher than that. So that's really hidden. We have only crystal and electric field. Okay. And of course, if you go this way, you can have something like that. Okay. So often cases you read in the literature saying that electric field can change the mobility of ions. This is definitely wrong. Okay, so because simply because in most cases, so this term is much smaller than KBT, then much smaller than direction migration. Okay. So this quantity cannot really have any meaningful change to the barrier. Okay, we're going to see later. There's only one special case where that you increase this into really big. Imagine that if I don't have the pellet, okay, if I have thin film, let's say this thing is only 10 nanometer, 10 nanometer, yes, something like 10 nanometer. Okay, then now here is 10 to the minus 6 centimeter. Then this can be something like 1 eV. It can be really large. Okay. However, what you are doing is essentially apply 10 volts across 10 nanometer sample. So it's very extreme, right? So even for modern semiconductors, you don't apply 10 volts to 10 nanometer thick sample. Usually the thing will break up. But anyway, so let's not worry about that. Let's worry when you have the normal case, how to understand the drift. Okay. So essentially, we are still using the same thing. Okay. So J is basically J from 1 to 2 minus J from 2 to 1. Okay. However, unlike this thing here, now you don't have the concentration gradient. So then the concentration for both position will be C. Okay. Will be C. Okay. I think I forgot something here. Is I'll write it here. So here we'll say 1 to 2 is 1/2 C1 eta gamma. Sorry. So this is basically the expression for the flux. Okay. So now you have the same thing. Tau. However, the difference is in tau because now because tau has the expression of the mu exponential kBt negative kBt migration barrier. Okay. However, what you see is that from 1 to 2, the migration barrier is actually smaller than the normal case, smaller than this one, because when you apply the electric field, you lift the position for state 1, right? Okay, so how much difference does that make? So the difference is that if you draw something here in the middle point, so this much is still delta migration. Okay. So what you do is essentially here you decrease by 1/2 of this value. So here you increase by 1/2 of this value. Okay. So here you decrease AE by this value. Okay. Then minus basically this one we have still the same thing as the same part, but minus potential or kBt delta migration. Now it's plus. Okay. So because from 2 to 1, the migration barrier is higher than delta H. Okay. Right, no problem. Okay, so what we can do is we can take this part out. Okay. So let's say it's 1/2 CA mu exponential minus kBt delta H migration. Then we have another part which is potential 1/2 the the EA over kBt minus over kBt. Okay. So we already said that the DE is much smaller than kBt if E is not very large. Most cases, only when you have very extreme cases, if you have thin films or at the interfaces, then you have very large electric field. Otherwise, electric field won't be very large, right? So if this is not very large, then the EA over kBt is much smaller than 1. Okay. So we know that when this is much smaller than 1, exponential x is basically 1 plus x, right? If I use Taylor expansion, right? So then in this case, this part is 1 plus 1/2 the EA over kBt. Now this part is 1 minus 1/2 the EA kBt. Right. And of course, 1 cancels out. And finally, you have this part times this part. Okay. Let's see if I'll erase this. So then we have the J drift is basically 1/2 CA mu exponential minus LH migration over KBT times the EAE over KBT. So this is essentially the expression. Okay. So another thing we want to write is we know that tau is this part. Okay. And we know that d is 1/2 a squared. Tau. Okay. So basically, we are still dealing with one-dimensional case, so it's basically the 1/2. Okay. So then we have this part is basically tau, right? And we have 1/2 a here, then tau here. Okay. Then J is basically what's left of it. We have the concentration left. We have then the 1/2 a and tau. That's basically due to any questions? It's basically due to COD. Okay. Let's see what left of it is basically V over QBT. Then we have electric field. Okay. All right. So you can already see this looks like this really looks like Ohm's law, right? So if I compare with this one with Ohm's law, which is this one, which looks very similar. However, we know that in Ohm's law we have the current density, which is charge flux, right? Which is Df times the J. So this is the particle flux in mole per centimeter square per second. So the charge flux Coulomb per centimeter square per second. Okay, there's a difference between that. Okay, let's see if that what happens when I take that. Okay, so I basically take this into this equation. We have CD df over kBt. Then the times E is basically negative partial x. Okay. So that would be our driving force. Okay. So of course we start off with the microscopic scale. So that's why you see all the constants are Kb or E. Okay. I can time it by Avogadro constant. Okay. We know that Kb times Na is what? Is R, right? So then we basically have RT here. Then E times Na is F. Right, so we have Vf here, okay. Then we know that this should be conductivity. Okay, so because it's already, we already get the microscopic expression for Ohm's law, right? So this part is your driving force electric field, or negative of the electrostatic potential gradient. Then this part has to be the conductivity. Okay, we know the conductivity is C, then mobility, right? So you could say this is equal to that one. Okay, so what we have is CD, then df over RT, v squared x squared. So this should be sigma, should be C, df, then mobility. Okay. You cancel out the C, this part. So what you left with, basically Einstein. So which gives you mobility and the diffusivity. with RP over Vn. Okay, so this is quite interesting because, so from the microscopic picture, we did not see anything about the mobility, right? Here we only care about the diffusivity, right? So the only thing up to here we have is only diffusivity, okay? The final part, we say, okay, this is conductivity. Then conductivity, we introduce the concept of mobility. You can already see that mobility really comes from the diffusivity. Okay, so this is really saying that this is really the microscopic origin of Lenzster-Einstein, which means that on the electric field, it's still the mobility which matters, which will give you the directional flow of your ions or your charged particles. Okay. So, and also you can see that here the electric field has absolutely no effect on the diffusivity, right? Here you can see that mobility and diffusivity, they are directly correlated with each other. There's no effect of the electric field at all. So what electric field does is create a tiny bit asymmetry in your energy landscape so that you have the directional flow. Okay. Of course, you can go back to here because the assumption we have is we say VEA is much smaller than KBT. You can highly expand these two terms, right? We can of course ask us the question: what if this assumption is not valid? So what if this thing is roughly equal to KBT? So this is really the case where you have where you start to affect your diffusivity or mobility using the electric field. Okay, let's just do the calculation. Okay, so then we can define a threshold. Okay, so this is basically threshold electric field. Which means you start to change the mobility or diffusivity by using the electric field. It should be KBT over VE times A. Okay. All right. So let's say I'll erase this part. Let's imagine that if you have a specific case, strontium titanate. We know that strontium titanate is a perovskite structure. Okay, so you have the titanium in the middle, then you have strontium. So the strontium occupying the corners, then the phase center. So these are the oxygen, right? So basically, in this case, oxygen hopping is from this side to this side, right? To the adjacent oxygen side. So we know that in the atomic distance, the lattice plane is 3.9 angstrom. Okay, so then A means that from this side to that side. Okay, so basically that's square root of 2 divided by 2 times dE is roughly 2.62 angstrom. Okay. Then if we want to change the diffusivity of oxygen in strontium titanate, even at room temperature, let's say 26 times 10 to the minus 3 electron volt for the KBT. And we know that oxygen has 2 electrons, right? Then A is 2.76 times 10 to 9. So because it's Armstrong, let's say I want to convert to centimeters. So I get something like this. Okay. All right. So let's say, because there's 1/2 here, okay, let's also put 1/2, 2, okay, times 2. So we can cancel something out, 2e cancels. 26 and 2.76, so that's roughly the same, because we only want an expansion. That's roughly 10, okay. And it's 10 to the minus 8, 10 to the minus 3, 10 to the minus 5. So roughly you get 10 to the minus volt per centimeter, or 1 megavolt per centimeter. So this is an extremely large value, okay. So which means that if you have 1 kilo sample, even the thickness is only 1 millimeter. So what you want to apply is 10 to the 5 volt to get this electric field strength. Okay, this is very large. Okay, normally you won't even think of doing something like this because you can easily electrodegrade or break the sample by applying such a big electric field. So any literature you see that claim they have a larger mobility or larger conductivity or larger diffusivity of ions because they have electric field, you have to take a closer look at the literature because it could be very wrong. Okay, so the only case is that you have the 100 nanometer thin film. You can also reduce it by 2 or 3 magnitude or order magnitude. Then it's probably better. Okay. All right. So finally, another 10 minutes. Finally, what I want to talk about is conductivity. Okay, we know that conductivity is basically concentration times dF times mobility, right? You also know that mobility, in our case, is very similar to diffusivity. Now we know that from atomistic scale or from microscopic scale, why that is the case. Okay, so then we can write the conductivity as the C times dF times the mobility is can be converted to conductivity. Diffusivity. Okay, D. All right. We know that D in this case is this part. Okay, so it has something to do with the hopping frequency. And then the hopping frequency is somewhat activated. Okay, so then D is D0 exponential minus KBT over delta H migration. Okay, so this is for ions. So for ionic picture, we have something like this. For electronic picture, only when we have something so-called tolerance, where the electrons are bonded to ions, we have something like this. So this is not usually true for electrons in valence band or conduction band, or electronic spaces in valence band or conduction band. Anyway, so we know that D0. So let me remind you, D is Cn A squared tau. Tau is mu exponential KBT migration. Okay. So we call it D0, which is basically a prefactor. Okay. So then we see this part except for temperature. So let me change to a different color. So there's temperature here. Otherwise, they are constants. Okay, I can call it sigma 0. T exponential. Okay, so if you have some Ionic species, for example, if you think about the oxygen vacancy in oxygen ions in YZ or lithium ions transport. So what you should really plot is basically log sigma T. Okay, if I put a T here, so this is sigma. So if I say log sigma T, right, so it basically log T sigma 0, then minus kBT delta migration. Okay. So then what you have is you have log sigma 0, then you have exponential decay. So if I plot it to 1 over temperature. Now we know that the migration barrier is basically minus kB divided by delta H over kB. Okay. So it's quite important that you have log sigma T here. Okay. So often cases you see people write just log sigma. Okay. Which is essentially wrong. However, you can get away with this if the temperature is not too large. Temperature range is not too large. For example, if you have only, let's say, 25 degrees C here, if you have 100 degrees C here, then you can calculate 1 over T. If not, difference is not too large. You can get away with plotting log sigma versus 1 over T. You still get a linear equation. However, the true linear equation should be log sigma T versus the 1 over T. So then you have these kind of, you can extract the migration barrier by measuring the conductivity of the ions as a function of the temperature. Okay. However, you have to be careful with that. So one final thing is that you have to be careful because here, for example, the C. So basically, the assumption is that the concentration is a constant. Okay. So basically, concentration does not change with temperature. You can do this kind of treatment. However, we know that, for example, we talk about, for example, the fractal pair. You have the oxygen vacancy, and you can have the cation vacancies. Okay, I mean, if you think about, you have the, for example, Franco. So this basically the concentration is, you can have the concentration of this as function of the temperature. So if you form the kind of intrinsic point effect, okay. Then in this case, the concentration is not a constant, okay. Then if you plot like this, what you get is both the migration barrier and also the formation energy for the defects. Okay. So this is the case often seen in highlight perovskite. So sometimes people plot log sigma or log sigma T versus 1 over T. And you have the kind of thermodynamic equation, and you extract the can be R or KBT, doesn't matter. You extract the enthalpy. Okay. However, for highlight perovskite or for other material system, you cannot really assume that the defect concentration is a constant. Now you have the formation energy times the migration barrier. So they are convoluted. You have to fix one of this to get these two things out. Okay. So otherwise you may have these kind of two things together. Okay, so basically, go back to this untransformed picture. So last lecture we talked about only the kind of high-level stuff, right? So essentially we talked about the fixed first law, which governs the diffusion, and then the Ohm's law, which governs the drift. And together we have this kind of very important, however, you don't see much in the textbook. You have this equation, right? So in this lecture, we talk about the origin of the in the microscopic picture on the diffusion, and we have this is basically P. We have this kind of expression for diffusivity. We know that also we talk about drift. We know that in drift, the electric field actually doesn't really directly change the diffusion. It basically creates a change in the any landscape. It's basically kind of keeping the balance. Then the ions start to move. Okay. And finally, we talk about the conductivity as function of temperature. And you can. So one important thing is that you can really measure the conductivity as function of temperature. If you get a plot like this, then you can get the magnetic barrier. So that's one important application. Okay.